sub u substitution. Substitution rule has many names. Very important rule. You're going to technically use this on every single problem in Calculus 2, a lot in Calculus 3, again, differential equations. So this one is extremely, extremely important. What is u sub? Well, the shortest statement is backwards chain rule. That's what it is. So we know that derivatives undo integrals, integrals would undo derivatives, and so on. If you have a chain rule, there should be an integral rule that undoes it, and that would be the u sub. So I'm just going to say chain rule, and then over here u sub. Now let's see what is this u sub and how does it work. So first I'm going to illustrate with a simple example, and then we'll move on to more interesting things. So integral of, let's say, x plus 3 raised to the 6th power dx. So you're looking at this thing and you say, well, the only thing to do this is, the only thing I can do is to actually FOIL this 6 times, right? And get some kind of x to the 6th polynomial, and then just work it out. But it's not that economical. So what you want to do is you want to take a look here and say, if this was one thing, and let's call it u, then I would just have u to the 6, which actually obeys the same rules as x to the 6, which would be x to the 7 over 7. So if I can actually take whatever is in parentheses, everything over here, and just make it a one variable, the problem would be much easier. So let me do that. U equals to x plus 3. Now the problem is that I have this dx to worry about, because there is x here and there is x there. If I change this thing to u, this cannot stay dx, because then I will have what we call dimension mismatch. We'll have the integral of u in respect to x, which doesn't work. So we also have to change that dx. And luckily, we can just differentiate our substitution and then make a differential out of it. And look at that. I have a u sub right here, and I also have to substitute dx to du. So now the new integral is u to the 6, and dx is the same as du, so just put du there. So now we go and see it's u to the 7 over 7 plus c. But the problem is that you have answer in terms of u. The problem is posed in terms of x, which means that you have to go back and convert it back. The sentence to remember is, so you can say this to every time, I don't care about u, I care about the x. And just substitute that in. So you like those sentences. And no one got it. So I have 1 over 7 times x plus 3 to the 7 plus c. And the problem is solved. That's it. Now I would like to take a look one more time at that formula that we had, e to the kx. So let's say e to the 5x dx. Now I know you memorized the formula. Yes. You mean 2 in front like here? Over here? Oh, we're going to take care of that very quickly. So we don't need this 2 now. We'll take care of that. All right, so let's try this problem. So you're going to say, you know what? Let's say I don't know the other formula. So I know how to integrate e to the x. So if this exponent here was just one variable, it would be easy for me to solve. So let's do that. U equals 5x, and then du is equal to, du over dx is equal to 5. And then move the x to the other side. And this is exactly what you asked. So now as I am substituting, I see that I can go and say e to the u, but then this dx, well, you divide both sides by 5, and you see it's du over 5. We know that constants can be kicked in front of the integral, and there it is. Do we all understand this? What happened? I'll explain it one more time. So now integral of e to the u is just e to the u plus c, and then we, right? I don't care about u, I care about the x. So 1/5 e to the 5x plus c. Now you were asked to memorize the formula that's going to be e to the kx over k, and there's that k, the 5, that drops below. But u substitution actually takes care of it. So you actually don't have to memorize the formula. So let me just explain this one more time so we understand it. So this is where we start, and we have 5x on top. And we don't like it. If that was just one variable, then integral would be easy. So we make that mess that we don't like into one variable, call it u, and we immediately differentiate that because we know that we will have to deal with dx as well. So you immediately differentiate, you make a differential, and then start substituting stuff. So 5x gets replaced with u, and the dx, well, dx is here, you see dx is not alone, so make it alone. Divide by 5 both sides, that cancels, and now dx is alone. So dx is d over 5. You plug it in. So it's a lot of plugging in. As soon as you are able to identify what the u is, the rest of the problem should be very easy and fast. You figure out what u is, you differentiate, you isolate dx because you will be plugging that in as well. That's like automatic immediately, as soon as you get u down. So now you have e to the u, dx, e to the u, du over 5, 1/5 goes in front and just becomes e to the u du. The integral of e to the u is e to the u plus c, and then bring back 5x, and we got the formula. So it's something like this you were asked to memorize before, and now you know how to do it. The same thing happens with sines and cosines. How about you try on your own? So try on your own using same technique, integral of sine 3x dx. So using the same method. So standard procedure, again, u is 3x, du over dx is equal to 3, du is equal to 3 dx, and then we'll divide by 3 both sides to get dx alone. And now we have sine u du over 3. We kick 1/3 in front of the integral, and all we need to integrate is sine u du. What is that equal to? Negative cosine u. So negative 1/3 cosine u plus c, which is negative 1/3 cosine 3x plus c. Sounds good? So some of the problems could be trickier. So the first one that I'm going to show here is this. Well, let's talk first about the concept in red, and then. So the way I figured this out, was easiest for me to figure it out, was to always look for function derivative pair. Function derivative pair. What does this mean? Well, let's take a look at the example and try to figure it out. When more difficult problems start, you might have, let's say, ln squared x divided by x dx. So you're looking at this thing and you go, whoa, right? Now, notation for this ln squared x, is the same like sines and cosines, right? That square there can be written like that. So this ln x is actually one unit, one thing. Now, when you look at this, you immediately notice that you have ln x there, and you also have 1 over x, because you can put 1 in the numerator, right? And you have over x. So think about that. The function is ln x, and its derivative is 1 over x. Because every time when you define the u, you will have to take the derivative. And if derivative is not present, right? Obviously, can't be done. So now, we are technically lucky. If I say u is equal to ln x, then du over dx is equal to 1 over x, which means that du is equal to 1 over x dx. Now, you see that you have that. See over here in a peanut? If you're allergic to peanuts, then I don't know. So in the peanut over here, you have exactly this. Maybe I should color code this. Let's go with blue. Have any blue peanuts? So now, when you do a substitution, you get u squared du. That entire integral reduced to a very cheap, very easy u squared polynomial. Because ln x is u, and that's squared, so u squared, and then 1 over x dx, the whole thing, the whole unit is just du. And from here, the rest should be easy. Integral is u cubed over 3 plus c, which is 1/3 ln cubed x plus c. Now let's say you are not lazy and you care. What would you do? You would take a derivative to check it, right? So what's the derivative? Let's change the color. What's the derivative of 1/3 ln cubed x plus c equal to? Well, we copy the constant, which is 1/3, take derivative of 3 ln x, which is 3 ln squared x, and then in a chain rule times 1 over x, and derivative of plus c is 0. These guys cancel, and you have exactly ln squared over x, which is right what you needed. Ln squared x over x. So it works. This is a good solution. It's a good solution because the derivative checked out. Does any of this make sense?
Would you have just use the power rule on this one? Like how you add 1 to the put it over your power?
So we transformed the ln question into a basic power rule, yeah. That's the power of the method. It takes something that cannot be done, actually at all, and transforms it into something that can be easily done. And then we just bring back the old variables and the old functions. So this is a transformation. We change the x domain into u domain, and then we do calculus in different domain, which because it's easier. These transformations exist across. There will be Laplace transforms in differential equations and so on. So there's going to be a lot of this stuff going forward in mathematics. And this is the first one, and it's the cheapest one of all, obviously, and it's also the most used one out of all. I would with confidence say 90 to 95% of your integrals in Calc 2 will use this to solve problems. And you'll be skipping steps. I mean, you'll be going from here directly there in one step because you'll be doing it so much. So there's nothing else to talk about here other than do 5,000 problems because it's so important. But look for function derivative pair. We have a function here, and we have the derivative in the peanut, which means that we were able to quickly set up. So let me do one more from the textbook. And then you do one, and then we'll, no, we have time, we can do it. Okay. So here's a cool one. I'll do this one. Oh, actually, no, maybe you can. X to the 9 sine x to the 10 dx. What do you think? Can you find function derivative pair? What's u? X to the 10. Because its derivative is x to the 9. Yeah, I know you're going to have constants to mess with, but that's okay. So as soon as you figure out what's the function derivative pair, you should be able to immediately set u to be the function. Its derivative, du over dx, is going to be 10x to the 9. And you know what? Maybe you are already ready to start skipping from the first step into differential, because this dx will always end up on the right anyway. Observe that we have the extra 10, so divide both sides by 10. And now these two guys are your du, and you have everything ready. Sine u du over 10 is equal to 1 over 10 integral sine u du. 1 over 10 negative cosine u plus c negative 1 over 10 cosine x to the 10 plus c. Done. A similar problem actually showed up on the second exam in the Calc 2 class, because we do this again. There's a trig section, two trig sections in chapter 7 for integration, trigonometric integrals, and trigonometric substitution, 7.3 and 7.4. So this stuff is coming back in Calc 2. And the U sub is one of the most important techniques. All right, so let's take a look how you're going to fare with this one. This is problem 20 in your textbook. I mean, all of this from the textbook. Square root of x plus 1 raised to the 4th divided by 2 square root of x dx. Let's see. Let's see what you can come up with. So what's u?
Root x plus 1.
Root x plus 1. Good. Okay, so let's take a look at this. U equals square root of x plus 1. That means that the du is equal to the derivative of square root of x, which is 1 over 2 root x. And then we put the x afterwards. So now we see this, right? That's that. So that's du. So 1-for-1 substitution. U to the 4 du. Done. We transformed a very bad integral into something very simple. So now it's u to the 5 over 5 plus c. And we say, I don't care about u, care about the x, which is 1/5 square root of x plus 1 plus c. Up to the 5th power. Yes?
At first, I did the substitution used just root of x, and then I tried to put a second layer of substitution. You can do that, right? And then just substitute each layer back in.
Yes. It's much more work, but yes. One more. (32) Integral of 8x plus 6 divided by 2x squared plus 3x, everything dx.
Is it 2x squared plus 3x on the geometry? Yeah.
Yep. That's 3x, yes. Shall we look it together? So tomorrow we're going to have this huge review, and we're going to take a look at, actually we still have to take a look at the definite integrals with u sub, because we actually will be changing the limits of integration. So we'll take care of that first, and then we'll go the comprehensive review, and final exam is on Thursday. So let's take a look at this. I'll get to your question as soon as. Actually, is it related to this question? I'm sorry? Yeah. Yeah. All right, so x squared has a derivative of x, and then 3x has a derivative of 3, which means that it looks like that u is equal to 2x squared plus 3x, and du is 4x plus 3 dx. Note my use of parentheses, because this dx is supposed to multiply both terms, not just 3. And now you can see that in the numerator, you can actually factor out 2 and get 4x plus 3, and you have your 2x squared plus 3x in the denominator. So now, there's the du. We have this 2 that is extra, we kick that in front. So what we end up with is 1 over u du. And that is what? Yeah. ln u plus c, which is 2 ln of 2x squared plus 3x plus c, and that solves the problem.
Instead of factoring out the 2 from the original integral, could you have multiplied by 2 or by du to make it 8x plus 6?
Yeah, but then you would have, then you would have 2 du. Sure, it will pop up there. Yes?
How do you determine that using the denominator of this problem? You know, the last problem that was in the numerator, how do you?
Function derivative pair, because this over here has higher exponents. And when you take derivative, exponents go down. That's why. So the denominator has higher exponents. Also, your du, just du, not the whole term, just du itself should always be in the numerator. All right, so I'll see you tomorrow. We'll do the changing of limits.